I'm just going to share my screen. Where is it? Ah, and share my screen. Can everyone see my screen? Yeah, or let me know in the comments if you can see it. That's perfect. So this morning's session is all about information visualization, which is also known as visual analytics. So this is a lead on from stuff I was discussing with you guys on Monday about visualizing the data. I don't know if okay, so sorry, I put myself on mute there. So an overview for this presentation is that we use charts, graphs, and visual interfaces such as dashboards, etc., to help provide a holistic sense of the data as we load and analyze it. So it can be in the forms of visuals, any sort of visuals, so different kinds of graphs, histograms, those dendrograms that I showed you last on Monday, and scatter plots, correlations, and a time series. These are useful to help us illustrate the performance of our algorithms. So in terms of seeing the efficiency of the algorithm in its runtime, in its data size, and also in terms of its parameters, its machine learning parameters. These are just a few examples of what we could evaluate for our algorithms using these visual interfaces. These sort of, I'm just looking at the chats. Okay, so excuse me. We can use these visual interfaces to help present information as part of, as I mentioned before, a dashboard. The dashboards are essentially figures that illustrate someone's performance. So I should have had examples here of dashboards. So this is how a company wants to look at how many total users they have, how much lifetime revenue, their repeat purchase rate to see how many repeat customers they have. And so this is an example of when they have it in just figures, but then they can have it in histograms, bar charts with different legends, a pie chart, a line graph, just to be able to see different types of continuing data, but also in data that isn't continuous. Another example is in this for a sales summary where they have different pie charts and different line graphs to depict the data that they want to visualize and understand a bit clearer. Another example of visualization, as I mentioned, were the dendrograms that I showed you on Monday. So information visualization as a field. The information visualization is an entire research field of its own. It's part of data science, but it's an entire research field. So as you are probably aware or are figuring out, that different parts of data science are broad in itself. The major groups at University of Washington are looking into are leading the way in this particular research field. And visual analytics can be defined as a science of analytical reasoning supported by interactive visual interfaces. So this broken down essentially means that the science of figuring out and analyzing what the data is telling us using diagrams and interactive diagrams to help us understand the data. So all in all, data analytics and human computer interaction, plus human perception, plus the graphs and other computer graphics forms information visualization. And this, I find this image sums it up quite well. So we need to have the data to help us map the visualization, but also to transform the data in, so, okay, let's take a step back. So we have the data, we transform the data into making it more structured, more normalized, and then to help us map the data and be able to visualize it clearer and this visualization should allow for user interaction. To help us increase our knowledge about what the data is doing, to help, which is also supported by the models that we generate to help create the visualization. We're seeing the question that somebody raised. We'll be using about Power BI in visualization, which tools we taught in this course. That is a question I think to hand to Ian, as I'm not entirely sure which tools are taught in the course. However, you can do a lot of visualization in Python. That's what we're going to be using as part of this hackathon, is using Python for visualization, but I think you can use Dashboard and other and there's a software that is on the tip of my tongue, but I can't remember the name of it. When I remember it, I'll put it in the chat. But for this particular hackathon, we're using Python. So the effective use of visualization for data science. As I mentioned previously, from the previous question, Python is quite a powerful tool for data visualization because it allows us to use Matplotlib and pandas together to plot our graphs and visualize our data. These are the libraries that I used for the dendrograms in the code that I showed you all on Monday. So, but this, you don't have to just use it for dendrograms. You can use it here, like in bar graphs. You can use it for line graphs. You can use it for the different different images to detect different heat temperatures to see where your data is leaning towards. So it's quite interesting. So, but when you are looking at data visualization, you need to keep in mind what kind of plot is needed, because line charts versus bar charts are for completely different uses, and whether the data that you're using is statistical or sampled. And also in terms of what ranges you need for the axis, because you don't want to have your axis too big if you just got small scales. And if you need to normalize the data, if your data is so broad and so varied, then you'll have to normalize the data. If it's quite straightforward between a certain amount, then that wouldn't need to be normalized. Just looking at the question. Okay. So going back to comparing bar charts versus line charts, we need to consider whether our data is categorical or whether it's continuous on the x-axis and choose our plots accordingly. If our bar charts are categorical, like looking at different companies, different car types, different colors, then this would be defined as being categorical, and would be you'd use bar charts. For line charts, this is for continuous data where you're having a continuous, say, monetary forecast, whether you're having anything that has a cumulative frequency. This is known as continuous data, and where each of the points in the graph are connected. These are for this is known as continuous data, and this is what you'll use your line charts for. Sorry. If I just go back, so if the data isn't continuous, the points are helpful to see. Just remember that as well. 1 point. So plotting and axis coordinates. How do we choose a minimum or maximum scale for our coordinates? And this is looking at linear versus log. Log is essentially when you normalize your data. So key questions when you have to ask yourself when you're looking at plotting of the data. Sorry if I'm looking at the phone often because I can't see the chat. I've got Teams on my phone as well. So every time a question pops up, I look at my phone. That's what I'm doing. I'm looking at any text or anything. So key questions to ask yourself when you're looking at choosing your axis minimum and maximum scales. You need to see what scale would give us the right intuitions about the phenomena you are plotting, and what lets the viewer visually compare and understand the phenomena. If you're having too large of a scale, this might lessen the impact. So it may seem that your bars are quite low and if all of your ranges are quite high, are quite varied, it may also be difficult to balance and actually see the type of get your accuracy from looking at the graphs, but also if your axis, hang on, what is the essence of, okay. So when you're looking at normalizing your data, you don't want to have, when you're looking at your data, you don't want to have too varied. So say if you have data that's between 0 to 2000, for example, for a reaction time. So from 1 second to 2000 seconds for a reaction time, that if for say 1,000 participants, that is going to be a lot of data to manage, and to visualize this data to be quite complex and not so user friendly. So to make it more user friendly and to make it visually more understanding for the human client, you'll need to normalize the data. This can be done through logs. So like 1 plus the log of that time, but there are other ways of normalizing the data, which we'll be looking at in today's lab. Which brings me on to the next slide, actually. So normalizing the data. This is one form of normalizing the data where you're limiting the values. So you're limiting your access to 2,500 minimum, but your values only go up to 2,400. If that makes sense. So you're normalizing the data to make it more readable. This is essentially what this lab is doing. This code is doing. So your comp 1, that's a company 1, and your company 1 value is 800, so it will be about there. And then comp 2 value is 5, comp 3 value is 2,400, and these are the ones in blue. But what we want to also see is a side-by-side plot of the alternatives. So we would put the alternatives in orange, but let me just take an overhead. So the alternative is the overhead DF value, if that makes sense. So we've normalized it, but and then if you carry on, the code continues. So to normalize the data even further, we get the alternative and divide it by the baseline value. And then we rescale that baseline value to equal the combined value in order to normalize the data. Don't worry if you can't understand the code. We will be doing some of this in the lab, which I think you received today. Can anyone first tell me in the chat what they think might be wrong with this figure here?
Aisha, the values like the x-axis and the y-axis should be equal. Like we have a scale for only 100, 200, and 500. It should be matching to the y-axis.
Okay, and anyone else want to have a go? Okay, I'm just looking at I'm just getting the. Okay, X scale isn't consistently spaced. Lack of information. Thank you for that. Well, let's see what the. So yes, you were right. All three of you were right who answered that there is inconsistency in scaling between the X entries and the Y axis. And also, one thing that I was hoping you'd pick up is that the wrong type of graph was used. Because this was continuous data, they should have used a line graph rather than a bar graph, if that makes sense. Because we want to look at, but obviously it wasn't it wasn't clear from the data that was given that it was continuous, but I think you can see here now that it was continuous because it's looking at execution time, if that makes sense. Let me know if you have any questions about this.
Sorry, is it also possible to is it wrong because we haven't got the we haven't named the y-axis?
That is also a good point. Because we haven't, so we don't know how much this execution time is in seconds or milliseconds or minutes or hours. So yeah, that's a good point. We know it's to do with time because our labels the execution time, but we don't know that measurement of time. So yeah, that's one point. Anyone else? I'm just looking at the comments. Yeah, okay, that makes sense. So other considerations that we need to remember when we're visualizing or presenting our data in a visual form is how easy is this data how easy can this data be interpreted by others? So if we go back to the example, we need to look about the scales. We need to have appropriate scaling from both the X and the Y axis. That shows the confidence intervals for the measures. It also needs to be quite readable. Say for this bar graph, for example, we don't know what it's saying. All we know is that it's a scale in a column of 100s. What is this 100 scale? And what is and like you said, how much time is this? Like 800 time. How much is it? Milliseconds, seconds, hours, minutes? We're not really sure, even for this graph as well. So it needs to be an adequate white space. So this essentially means that the plots need to be large enough and spaced enough in order to distinguish between the different plots on the graph. Also, the font size needs to be at least 20 points for presentations or 9 points for paper, just to allow the human eye to actually see the individual points on the graph. It needs to, the color needs to also be appropriate. So we had to pick visually distinctive but tonally compatible colors. So if we go back to, say, this graph, blue and orange are completely contrasting to one another. So it's easy for us to judge between the two different groups. However, if we use to visualize. So you also have to think about using light text on a dark background or vice versa, and be quite wary about using red or green or colors that form other types of color blindness, as we need to make our data and our visualization of our data more accessible for a wide range of people. And there may be people out there using good data or using these visuals that may be colorblind. It also, you think about the printability of the data. Okay, that makes sense. Okay, so you also need to make sure that the colors can be read even if it's in grayscale. So say if companies can't print off in color, it needs to be distinguishable in grayscale, and that your shapes have solid or dashed outlines so they can be distinctive when printed, so they can actually see the plots. We've been using Matplotlib and Piper have been used for many visualization tasks. They've been used for scatter, line, bar chart, as we've been discussing, and can overlay into other imaging such as bitmap images and base map images, or even heat map images as well, to map your data and to actually visualize the data to see different temperatures. So they say the lighter parts of the, if it's more brighter in some areas and darker than some areas, you know that's where most of your data lie in a heat map. This library is very powerful because it takes in NumPy matrices, lists, and also pandas data frames, and it supports computation into subplots. So these are just some examples of different visualizations that you can use in Python. So this is a line graph for which is similar to the cumulative accuracy profile graph that I showed you guys on Monday. This is another grouping graph that you can use. Essentially, and this is another line of best fit graph, plot regression graph, and also a heap map or bit mapped graph too. So these are all graphs you can develop in Python using the libraries, and these are some more graphs you can use, including putting the box plots into the graphs to make for more accurate reading. Although, can anyone tell me here what may be a problem in the graphs that I'm showing you on this slide?
I think he's going the opposite direction. Is he reverse engineering?
Yeah, because I think this one was to do. I was talking more about the visualization of it, like the colors, because like the red and the greens might be difficult for people, because we need to make sure that it's it was that contrast. Yes, that's right. But yeah, this was looking about the reverse engineering side of it, but it was more looking at the colors, because this might be difficult. This wouldn't be appropriate when presenting your data to the wider public. So a summary of the general rules of thumb when it comes to visualizing your data, you need to think about the dimensions, you need to think about your axis, your scaling, your labels, your colors. Have I presented my data? Have I mapped it into a meaningful, in a meaningful way? Use the right types of graph for the right types of data in terms of being categorical or continuous? What is the phenomena that I'm trying to compare with the other? So say here in this graph, even though the colors aren't right, this phenomena is clearly depicting the scores between men and women. So this wouldn't be appropriate for a line graph. It would be more used for a bar graph as it's shown right here, because it's categorical rather than continuous. Do we want to show two or more items side by side in the same scale? Another aspect you have to remember is understanding what the underlying phenomena is. So you need to, before you plot your data and visualize your data in different graphs, different images, you need to be able to understand what it is that your data is telling you, and be able to understand what the right scale and coordinates should be to show the intuition of the data, because you need to make your data intuitive, meaning your data, you understand your data, but you also need to know how to make your data readable to everyone else, for them to intuitively understand, this is what the data is talking about. And also, if your data is too widespread, to think about whether to normalize your data or not. So this is when the topic comes down to visualization in machine learning. In the next session, looking at machine learning, and we'll revisit this in the next session later after this. But when it comes to visualization of what algorithms work best, what in terms of plotting different strategies in accordance to different performance measures. So I don't know if you remember if you go back to the previous slides, looking at illustrating our algorithm's performance. So looking at all these different aspects of our algorithms can be plotted using visual interfaces. Go back. Which hyperparameters should I be setting? We have to plot our parameters at the performance, which one's the most optimal of the parameters for visualizing our data. How many dimensions are inherent in the data, and how much data should I use for the training to train the machine for the learning algorithm, and how much data should I be using to test the algorithm? I don't know if you guys remember when I showed you my test sampling, test train data for the cumulative accuracy profile on Monday. I showed you guys my code. For mine, I split my data in half because I had about 120. So I wanted it to be equal. So I split mine in half, but then because So that was 120, so 60 for the testing and for the training, and 60 for the testing of the algorithm. But then I discovered that if I used 25% of my data for training, it gave me the same result when I tested it. So this is looking at the most optimal use of your data to look at which how much data do I need to use optimally to train the data, and will it make much difference if I reduced it? What impact will it have? So, but all of this is upcoming. But the fundamentals of visualization are looking at a key question is, we've gone over some of the basics of choosing different factors of visualization, looking at the appropriate axis, looking at whether we need to normalize our data, and determining the type of plot required for the type of data that we have. But is there a more general set of principles for choosing and composing different features to pick a particular visualization? There was a study going on, known as a theory rather, called the grammar of graphics, by Leland Wilkinson, for R in 2005. And this divides the plots into different layers using data, aesthetic mappings, geometric objects, statistical transformations, and position adjustments. So these are your different layers of your data. And they also include scales, coordinate system, and facet groups in order to structure your data for appropriate plotting. Examples of statistical transformations and geometric mappings include histograms, smooth plots, box plots, density graphs, frequent polygraphs, also statistical relevance such as bin maps, smooth maps, box plots, and bar graphs, line graphs. So as you can probably see here, box plots do fit into both statistical and geometrical. Histograms, the binomial side of histograms are statistical, and the actual visuals. So the binomials, when I talk about binomials, I mean the actual figures such as p less than 0.05. When you're looking at a normalization of growth, those are your binomials, and those are under statistical. So statistical is looking at your numbers. Geometricals are looking at the actual images and the plots itself. So in Python, there is a library called ggplot that emulates ggplot2 in R, and you can use this directly by just importing it to create your visualizations. Just looking at. Yeah, it is necessary to split your data to test and train it. It is definitely essential to split your data in order to improve the performance and outcome of your algorithm. So going back to my work when I did the cumulative accuracy profiling, if I didn't have enough to train my data, the algorithm would have been the accuracy of my algorithm would have been incorrect. Then we wouldn't know anything about the algorithm. We wouldn't know if it's testing and training is a part of evaluating the algorithm. Because it needs to be in 20. I was looking at the comments, sorry, because I can't see it on my screen here. So open up Teams. Just looking at questions, I can see there's a debate going on. Oh, what if we didn't split during the ratio 25 setting? Yeah, 25% train. So when you test your data, when you're testing and training your data, you want to do 25% of your sample for training, I know I started off at 50%, but then I realized that 50% and 25% gave the same results. So standard is 25%. And then you have testing of your data is 75. Okay, so a bar chart represents data that is categorical. So looking at, if we go back here, for example, looking at the difference in performance between men and women. So between the two different gender scores. Anything that's not continuous. So here in this data is rather continuous. That's why it's in this sort of graph. However, this the data isn't continuous between the two groups. If we go back here again, even this sort of graph isn't appropriate for continuous data as the X categories aren't correctly categorized. But if we go back here, because we're splitting we want to see the difference in performance between the three different companies. The three different companies aren't connected, so they're not continuous data. We want to look at comparing company 1, company 2, and company 3. That's when you'd use the bar graphs, and this is known as categorical data, rather than continuous, if that answers your question. Just keeping an eye on the time because this is supposed to be an hour and a half, but I've only got an hour today. So if we go. So with machine learning, we can also use it to semi-automate the process of choosing the right visualization. So to some extent, there is software called Tableau, which is the software that I forgot the name of, and I remembered it now. It's Tableau to help you automate the process of choosing the right visualization techniques. And there are other more advanced visualization in Python beyond MATLAB, as MATLAB doesn't focus on data that is statistical in nature, so it doesn't show the confidence intervals or correlation. If you want to be able to show these statistical areas of your data, you want to use Seaborn, which are Matplotlib and PyPlot extensions for I can't say the word, statistical data in Python. If you want to know more about if you want to know more about Seaborn in more detail, there is this website, but we are going to go into it more in this presentation for plotting data with Seaborn. So Seaborn, as I mentioned before, is an extension of Matplotlib with built-in themes for colors, for visualization, for visualizing univariate and bivariate distributions, tools for linear regression, matrix visualization, statistical time series data, and for grids of different plots. So what you would have to do is import NumPy, import pandas, import Seaborn, and import Matplotlib and matplotlib.pyplot. You can develop scatter plots with Seaborn. So this is some simple data of random points. So you have 150 points with a linear slope of 0.3, with X being the array of your different range of different points. So this is a randomly generated randomly generated plots using the categories, using the variables we set. It's just to help because we need to use pyplot, we need to first of all import matplotlib and then import my pyplot separately in order to plot the graphs. And so after we plot we got our X points, our X values, we will plot these. So in the y-axis, so times by 5 plus x times the slope. Using a mathematical formula, and then we want to then on the z-axis map the point. It is, but you have to explicitly call it. And then, so essentially this will then plot the points. So if, and give it different shading depending on if a Boolean is true or not. So this is your line graph here. So your line of best fit, sorry, not your line graph, your line of best fit, based on the random points that were generated in your graph with Seaborn. So Seaborn is quite a powerful tool. It also helps, Seaborn would also help you understand your data relationships and how, so looking at, in this context, is looking about how much people tip. So it's a simple piece of code to help you see about how much people tip. So your question is how do people tip on different days of the week? So you're putting your different variables here, and then you're creating a graph for each time value. So looking at how much people tip at lunch versus dinner, and then you're plotting your total bill versus the bill with a tip within. So total bill versus the tip within each graph, and then you'd develop it as a scatter graph. So here you can see that we do have some outliers, but the tips are greater for more varied at dinner rather than at lunch. So it can help you. This Seaborn can help determine the relationships at different times, like essentially how it shows here, making it a lot easier to visualize rather than having both times together in the same graph. This is another way that it can be done to help visualize it a lot clearer, to untangle the scatter plot, essentially. I'm not entirely sure what the difference between random, I have to be honest, I use C# and C++ a lot more often, but I think this is something you could ask Ian or Bashir in the next session. But with Seaborn, instead of it being so visually constructive and visually difficult to read in the scatter graphs, you can actually split the scatter graphs into different sections based on size. So you can actually read it a lot more, because this sort of method of visualizing the data is a lot more easier to the eye and a lot more intuitive than the graphs down below. Can you guys see that? So looking at different pair grids now, so pair grid comparison. So let's look at how different factors are influenced by the size of the party. So we've got the scatter size and the hue size. So can you see here how it can change depending on the size of different people at different times? So yeah, this is looking at different heat maps. So I use Seaborn to develop a heat map, and like I said, heat map is essentially this, where you the greater the data, or say the greater the cluster, it's going to be the brightest part of the map. So the brightest part of the map where most of the data is focusing, or when more of the data, when you normalize it or structure it, is plotted in this this remit. So it's going to be above 50, and the total bill here, the majority of them is between 13 to 18 pounds for the total bill, and the next would be between 8 and 13, and then the next most popular bill category is 18 to 23, with sizes if the size of the party is 2 people. Those are the most common. So here we can determine that the most common party size was 2 people when they went for a meal, and the most common bills were 13 to 18 pounds, with the second most being 8 to 13, and the third most being 18 to 23 pounds. You can also use Seaborn for your box and whiskers in your box plots to accurately show your outliers, exactly where the bar charts or your plots are located on the graph, your upper quartiles, your medians, and your minimum ranges. Seaborn builds upon Matplotlib with a focus on statistical data, so not just the visualization, not just the geometrical side of things, but it also uses it focuses on the statistical side of things. So if you use it with scatter plots, it allows it for fitting and confidence intervals to be able to understand the trends that your data is showing. It provides grids for finding attribute to attribute correlations, which is incredibly useful for finding correlations by eye, because correlations through statistical calculations is a lot more challenging manually than if you see it visually. Just looking at the questions. Any questions again? Okay. So the heat maps, like the one we have here, shows the most popular aspects, and the box and whiskers show where data is commonly distributed. Each of these has an important place in data science and data analysis. So now that we've finished that, we have half an hour. That's great, because we can go to the lab. So if I just open the lab, download. Have you guys got the lab moment? This all makes a lot more sense once we go to the lab app. I just file, new notebook. My internet's really bad today. File, upload, choose file, open. So your lab should look like this. Let me know if you do. Do you guys have the lab? We're going to go through it anyway. Can you guys see my screen still? Okay, that's fine. So now we're going to have a go at visualizing our data. Have I got the right? Yeah, I got the right one. So first of all, as we mentioned in the lab, in the slides, we need to install our libraries. So these are already been installed already, but I just thought we'd just double check that it is. Here are some imports that we'll use for the notebook, collected here for simplicity. So we're importing our date and time, our current date and time, the URL library. We're importing the all-important pandas for our data frames and our machine learning operations. We import our NumPy library for our array operations, SQLite for simplistic database analysis. We're using Scrappy for multiple web pages, and importing Swifter to parallelize the computation. We also want to import py strings in join and string matching for approximate string matching. And for data visualization, we import matplotlib and importing LXML for download and parsing. So first of all, we need to acquire our data. I live on a hill, you see, so it slopes every so often. So first of all, we acquire our data about companies and CEOs. So our data would be using a GitHub a CSV found on GitHub, and we assign that data to our company data frame. We then persist that data into an SQLite database to be able to read it back to us. So we do that by using the variable bear with me. Okay, creating a variable called con if with SQLite to connect to the local database and in order to read that database back to us. So this is the data that we are working on. We are working with, so different multiple URLs, different markets, different fundings, different status in terms of whether it's still operating or not, and where they're operating. And if I can go to the right bar, where it's operating, what type of funding it has, where it's being founded. So it's a range of essentially it's a range of different data regarding different companies. Now we need to read the data as a HTML table containing information about the CEOs. So we do the exact same thing as we did there. So we create a data frame in order to read the data, read the database to be able to give us the information about the CEOs for the different companies mentioned in the previous table. To get a bit more complicated, we then need to extract the structured data. This is done by, so essentially we need to find, in this example, we're going to find the date of birth for the CEOs. And we're going to be doing this through a technique called crawling and scraping data from Wikipedia. So in order to do this, we need to create a list of CEO web pages to be crawled by appending the executive name onto the Wikipedia HTTP address. So first of all, we obviously need to create our crawl list, and then create a for loop. You can probably tell that I work with C# a lot more because I'm more used to using these to comment rather than the hashtag. But we then need to create a for loop crawl through the websites on the GitHub database. Okay, yes, I'm going to go through that now. Okay, so this is looking at for each of the executives, so that's each of the CEO web pages in the excuse me. So each of the executive for each executive, so each CEO in each of the items in the database that is under the, I think I've got people confused. So if I say executive is the variable that we've defined within this for loop, and this executive, it can be you could have named it X, Y, anything. So for X in the database that we have in the company CEOs database, which is this one here, we want to loop through the column that is under the executive. So essentially what we're doing is we're looping through this executive column here and generating these websites. So say it loops through the first item, so for Julie Sweet, and it develops this HTML here. So what it does is it loops through the executive, each item in the executive column, and then adds to the crawl list that we have here it adds this line of code, this URL to the crawl list, and adds the name of the executive at the end of that URL, if that makes sense. So it goes through all of the executive names in sequence. So say it goes to Julie Suite, adds Julie Suite to the end of this URL, and then adds this URL to the crawl list, and then does the same thing to all the others, if that makes sense. Nobody has questions on that. I will go to the next bus. So it does it for every single item in that list. Okay. So now we want to crawl each website in the crawl list. So in our list that we have here, we want to crawl through each of these websites in order to obtain the HTML content and store this HTML content in a list called pages. So we use URL lib to crawl all pages in a crawl list to store the response of the page in list pages. So we got our list called pages here, and this is where we're going to store our HTML content. Again, we need to develop a for loop, which in this case will be using the URL lib. So for URL in crawl list, so for each web page in the crawl list, we want to extract the person's name at the end of each URL. So looking at extract the person's name, so it's the names at the end of these URLs all here. Where am I? And then we want to print the statement. We're looking at the file for this executive. So essentially what it does is it prints out the statement for the first item first. We're looking at the file for juliessuite.html. Then we want to split the URL into different parts and convert the person's name into ASCII code. You do this by using URL list, which we created earlier. URL list, which is a new list that we're creating. That's why it says list here, and we're defining it as a list. And we're using URL.library to parse and split the URL. And we're using the second item in the URL list to quote and then URL lib.parse.quote and then URL list2. I know it has confusing, but all we're doing is splitting the URL into different parts and converting the person's name into ASCII code. And then it attempts to open the page using what we've assigned here, and then it prints. However, if there is an error, this statement will be true. So this is what it will find instead. So this is essentially what we wanted. So we got the looking at file, and then we have it converted into ASCII code here and put into our pages list, just as we wanted here. So this is the URL splitting. This is what we're looking for. So HTTP client at HTTP response at, and then the ASCII code. This ASCII code is the the person's name. So this is our URL, our list of URLs, and we're using that to convert it to split the different aspects of the URL first. That's all we're doing first, is splitting the URL. We then convert the second part, the name part, the executive name part of the URL into ASCII, and then save it into the pages list. which is here. That's all we're doing. We're just splitting the URL into two, and then converting the executives' names into ASCII, or the person's name into ASCII, and then saving the overall URL with the ASCII version into the pages list. If there is a problem or if there is an error, it will print error and the reason for the error. And then, so to populate a table, yes, sorry, from what we already have. So why don't we just split if we could extract the executive column from what we already have? It's to make the machine understand what it's doing. It's more for the machine than us. You'll see now. So then, after we've split the data, what have I done? After we yeah, you can import a URL list from an Excel CSV file. So we then want to populate a table with the name, web page, URL, and birthday of each CEO. So for this, we use etree.html on the HTML content of each page to get a domain tree that can be processed via XPath to extract the birthday information and then store that CEO name, the web page, and the birth date into a single executive data frame. First of all, we need to first check. So we've got an executive data frame here that we're going to create that has the executive's name, their web page, and their date of birth. First of all, we need to check whether the HTML content has a table of type vcard. It's a web page based fundamental. We then extract the birthday information. If there is no birth date, the date time value would be NAT, which is not a type. So if there's no birth date on the available on the website, it will come up as basically this doesn't exist, and it will go through all of that for the extraction for all the executives. Sorry, and for some reason this does. That should have worked. Oh, hang on a second. Let me just run all. Bear with me. I think someone's been using this code because this should have worked. Bear with me. My Wi-Fi is a little bit slow. Just reload. There you go. Oh, okay. It doesn't want to play ball with me today, so what I'll just do is I'll just go back to Colab. It's my Wi-Fi. Apologies, guys. So file, upload, choose file, open. Great. So it's back again. So then we want to clean and manipulate the data in the tables. So this is essentially what we want to do is we want to join the data that's in the executive data frame with the data that's in the company's, the CEO's data frame. Yes, definitely. As a computer games developer and AI developer myself, I would really suggest a desktop is better than a laptop, but there are some laptops that are powerful out there, like the HP Omen, but a computer's a lot better. A desktop computer's a lot better. So we want to combine the data from the two data frames. However, if we look at the data frame, the executive data frame, we'll notice that the name exec underscore DF has underscores, which won't match the names of the executives in the company, in the names of the executives in the other data frames. So if we see here, Julie underscore suite, the other data frame doesn't have an underscore. So we'll take a look at the name and born data in executive DF, and we'll do this via projection. And we also notice that if we go down to row 20, if we, some special characters may cause issues. So we're going to see about how to accommodate for those. So we first create we first of all open up our data frame, and with the categories for name and born. And so our name is Julie Sweet, and born, there was no date of birth available on that site, so that's why it's NAT. And then it does that for all the other executives. We then clean by removing the underscores and store this data into a new field called clean name. So this line of code here essentially takes, creates a new row, a new column called clean name, as we see here, and it uses the name in the executive data frame, so like Julie underscore suite, and it uses this line of code to then replace the underscore with just a space between the two names, and then assigns it into the item in the data frame, if that makes sense. It does that for all of the executives. So essentially, this line of code just removes the underscore so that it matches with the date, with the names that are in the first that's in the CEO data frame. We can do the same thing in SQL. So that this is an alternative way of doing it, where you just, all you need to do is open up the executive data frame to SQL, and then it creates a temporary variable called temp underscore exec, and so temp is, no, it doesn't, excuse me. So if in each of these executives, if in each of these name values here, if it includes a underscore, it replaces underscore with a space. It's the exact same thing here, just in a different way, and it's the same amount of code as well. It's well as one more line of code, so it'd be easier just to do it this way rather than this way. If you want to use SQL, this is the way to do it. And then so you have the name there. So if we want to then put it together, so now that we've cleaned it, because we've cleaned the name, making sure that it hasn't got any underscores, we then want to put the two data frames together. We start this with a simple join between the two data frames and persist it into the database. We can check then how many companies didn't have a match on the CEO name. So then, we're opening the company's data frame now and merging into it the executive, from the executive data frame, the clean name that we've just developed, the date of birth, into the executive column. So based on the executive column and creating comparing the executive column with the clean name column. So essentially what it's doing here is it's putting in the clean name and the born or the date of birth of that executive into the database for the company CEOs. for that, you'd create an if statement or a case statement. If a name does have an underscore in it anyway, which most of them don't, because it'll have a dash but not an underscore. But if it does have an underscore, that would be you do an if statement to ignore that particular item. So what you'd do, so what this has done is it's imported all the clean names from executive and all the date of birth from executive database and put it into the CEO's database. Not a problem. And then it's printing off the database. This is to test whether this has actually been assigned. We then create a merge data frame using the CEO's data frame. This part's completely optional. So using the same thing that we did here. So this is another way of doing it. So this is the easiest way to merge it in, but there is this other way of merging where we create a new data frame. We put into that the company's data frame and then merge the executive data frame aspects into it. And then we tell it to print out the clean name or anything that we want. So in this case, we want it to print out the clean name column. Yeah, I'm just finishing up, Ayesha. Sorry, Ian started it a bit late. This session was supposed to be an hour and a half, but he took up some of my time. So just give me a few minutes, and I'll be nearly finished, if that's okay.
Yeah, sure. Please move ahead.
Sorry, it is because my session was supposed to start at 10 o'clock, but
Sorry,
Ian
I didn't
went
know that. Yeah, no worries. Take your time, okay?
Thank you. Thank you. So then we also we want to see if the date of birth. So sorry. So we then look at the company's data frame, put that through SQL. If a certain aspect exists, then we'll want to replace it. So essentially, here it's looking at the date of birth. If the date of birth does exist, so say for Julie Sweet, her date of birth didn't exist, so it'll be classed as none. But if her date of birth exists in the company's column, in the company's CEO's data frame, but doesn't exist or does exist in the other column, it would be replaced in as you can see here. And the same thing with the company name as well. And then we go. I've nearly finished. I think I've got. I'm trying to go quickly through this. But where is me? Where is it? So then we then go through the process of finding the missing aspects. So this compares whether an aspect is missing in both, or if it's missing in the left in one type only. To then neaten it up, it does that there, and then when we looked at the names of the CEOs in the executive data frame, we also noticed that some names had special characters, and this could also be used to help that question about names that do have an under score in that name itself. So this is using validation rules. So you'd use these if statements to ensure that those names aren't overlooked, or if there are illegal names. I won't go through this because I'm trying to save a bit of time. Okay, no, this is important. So we then do a similarity join by seeing which columns from both are the same, and because if we don't want duplicate columns, so this will just remove the column that we don't want. And then finally, we'd have the company info and the CEO info all together in one data frame. This then takes our data frame that we created here. So as you can tell, it's a lot of human work that we have to do. So our data frame that we created with all of the data. Oh, it's going to have the error. I'm not sure why this. Oh, yeah, I know what the error has happened. Yep, sorry, ignore me. It's not a problem. So we've got this, and we want to look at different categories. So this is essentially looking at the date of birth, the company, and the executive of the company. And then we want to see how many of those executives were born on a particular day. So none of them are born on the same day. So it's all ones on that side, in this column. They could do that as in counting using, and you can do it in SQL as well. So you can do it either in normal Python, or you can do it in SQL as well. You can group each individual, and then what we did was, after we've gathered all of the date of births and how many people were born at that particular time into a table, we can then group that into into different groups by who was born in which decade. So then, and this is where we see about different types of data. So this grouping the individuals isn't a continuous data, because they've been born. We now want to cluster them into different groups. So it would be categorical data, which would be more suited for bar graphs. So we'd group them using this code and then plot it into a bar graph to show that we had 4 people born in the 1950s, 7 executives were born in the 60s, with 1 of them being born in the 1970s. And when in your free time, because we've run out of time now, but try and take this one step further and try and link the companies table with another data set to determine the market for each company, and try and measure whether there's a correlation between the kind of company and the age of the CEO. This may use a different type of graph than what we have here, but that would be something you could try in your. I hope this has made sense. Sorry if the ending of it has been a bit rushed. It's only because I didn't have all the time given to me for this topic, but I hope you guys found this useful and easy to follow in terms of visualizing data. I'll just stop sharing my screen.
Thanks, Ayesha. I'm just going to stop recording there
yeah,
so that we can
that's
save that and have